So in today's lecture, we're going to be going over a couple of problems from each of the lectures that we've looked at within the past 3 days. So there's a lot to cover, and if you guys have any questions at any point during this lecture, please feel free to ask me to stop the video, and I will happily go over any details that you want me to go over. So we've got a lot of ground to cover, so let's begin. So these first couple problems are going to be from the first lecture. So it's going to be on, the mathematical basics as well as unit conversion, with more of a focus on unit conversion. So example 1. Example 1. So example 1 says that the mass of a parasitic wasp, I don't know why I chose that, is 5 times 10 to the negative 6 kilograms. 5 times 10 to the negative 6 kilograms. So this problem is asking, what is this mass? In units of grams. Part B is asking for this mass in units of milligrams. And then part C is asking for micrograms. Micrograms. Very good. So let's begin. So for part A, well, we need to know the relationship between kilograms and grams. So our mass is 5 times 10 to the negative 6 kilograms. And furthermore, we know that 1 kilogram is equal to 1,000 grams. 1,000 can also be written as 10 to the third power, right? 10 times 10 times 10 grams. So we're going to use this information to help us out, right? So we're trying to go from kilograms, to grams. So if I divide the left and middle side of this equation by 1 kilogram, we get that 1 is equal to 1,000 grams in 1 kilogram. If you guys remember, unit conversion is just multiplying by 1. So we have that our mass, which is 5 times 10 to the negative 6 kilograms. When we multiply it by this conversion factor, which is 1, right here, right, we got 1,000 grams in 1 kilogram. So the units of kilograms up top get canceled by the units of kilograms on the bottom, and then we're left with an answer in grams, which is what we want for part A. So this is going to be equal to 5 times 10 to the negative 3 grams. All right, so this is our answer for part A. So part B is asking for this mass, this 5 times 10 to the negative 6 kilograms in units of micrograms, or excuse me, milligrams. So for part B, the unit conversion that we need is going to be that 1 kilogram has 10 to the 6 milligrams in it. So 10 to the 6 is also 1 million, but it's just easier to leave it like this. And so dividing both sides by 1 kilogram, we get that 1 is equal to 10 to the 6 milligrams, or million milligrams, is in 1 kilogram. Right. So this is our conversion factor. So then we have our mass which is 5 times 10 to the negative 6 kilograms. Make that a little bit cleaner. So 5 times 10 to the negative 6 kilograms times our conversion factor, which is this right here, which is 10 to the 6 milligrams per 1 kilogram. And so we have 5 times 10 to the negative 6 kilograms times this conversion factor. So the kilograms cancel out, just like before. And so we're left with an answer in milligrams, which is good. So we have 5 times 10 to the 6, or 10 to the negative 6. So this is effectively 5 divided by 10 to the 6. Actually, let me just rewrite that. So this first thing in parentheses is equal to 5 times 10 to the 6. 5 divided by 10 to the 6, excuse me. Multiply by 10 to the 6. Units of milligrams. And you see that the units of milligrams remain, and these 10 to the 6s end up canceling out, right? Because in this first one, you're dividing by 10 to the 6, which is million. And in this factor, you're multiplying by 10 to the 6, or 1 million. So you have a million divided by a million, which is 1. And it turns out that this mass in milligrams is just 5 milligrams. That's part B. All right, so last but not least, the problem is asking us to find this mass in terms of micrograms. Here, micro. So micro is usually denoted by mu. Right, it looks like this weird curly M thing. Let me draw it. There we go. And this is units of, or not units, this is on the order of 10 to the negative 6. So the unit conversion that we need, the information that we need to do this unit conversion is that 1 kilogram is equal to 10 to the power of 9, or a billion, micrograms. Right? And so just like before, I'm going to divide both sides by 1 kilogram to get that 1 is equal to 10 to the 9 micrograms per 1 kilogram. Right. And so now we have our mass, which is 5 times 10 to the negative 6 kilograms, multiplied by our unit conversion factor of 1. So we have 10 to the 9 micrograms divided by 1 kilogram. And the kilograms cancel out. And then this becomes, so again, converting this first thing in parentheses, this is equal to 5 divided by 10 to the negative 6, or 10 to the 6, excuse me. And then we have 10 to the 9. It's going to be in units of micrograms, because that's the only thing remaining after our unit conversion. And so this is equal to 5. And if I group this 10 stuff together, right, we have 10 to the power of 9 divided by 10 to the power of 6 units of micrograms. Well, 10 to the power of 9 divided by 10 to the power of 6 is equal to 5. Well, this whole thing is equal to 5 times 10 to the power of 9 minus 6 micrograms. So this is going to be 5. Actually, I don't even need parentheses. This is going to be equal to 5 times 9 minus 6 is 3. So this is going to be 5 times 10 to the 3 micrograms. So this is saying that our mass, the mass of this wasp, is 5,000 micrograms. And that's it for this first problem. All right, now let's move on to the second problem from lecture 1. I'm going to zoom out just a little bit. Scroll down. So example 2. All right, this is still from lecture 1. So the second example says that the depth of the ocean, is sometimes measured in fathoms. Sometimes measured in fathoms. And the problem says that 1 fathom is equal to 6 feet, because why not? So the problem goes on to say that distance on the surface of the ocean, so distance on the surface of the ocean is sometimes measured in nautical miles. Is sometimes measured in nautical miles. The problem also tells us that, 1 nautical mile is equal to 6,076 feet. Okay. So the problem continues that says the water beneath the surface, beneath a surface rectangle, of 1.2 nautical miles by 2.6 nautical miles has a depth of 16 fathoms. Has a depth of 16 fathoms. So the problem wants us to find the volume. Find the volume of water in cubic meters beneath this rectangle. All right, so we're really dealing with like a cube of water. So I'm gonna try and draw a picture. So we have, I don't know, lines that go like this, and lines that go like this. Something like that. Try and make it look good. There we go. Drawing a cube. You go up. Like that. It's not gonna be the cleanest looking cube, but that's okay. So this says that, one side is 1.2 nautical miles. I'm gonna abbreviate that as NAU. And another side is 2.6 nautical miles. And then apparently the depth is 16 fathoms. Right, so now the problem is asking for the volume of this cube. In units of cubic meters. All right, so we have a lot of units to convert, so let's get started. So let's write down the unit conversions that the problem tells us. Well, the unit conversions that the problem tells us are that 1 nautical mile, which I'm just going to leave as NAU, is equal to 6,076 feet. 76 feet. Additionally, 1 meter. The problem doesn't tell us this, but I looked it up on Google. So 1 meter is equal to 3.281 feet. Right. And then last but not least, we have that 1 fathom. 1 fathom is equal to 6 feet. So what we can do is we can convert the length, width, and height of this cube into units of meters, and then multiply, all those lengths in meters together to get a volume of the cube in cubic meters. So let's start by looking at the length. So the length, L of this cube, is 2.6. 2.6 nautical miles. And we'd like to convert that first into feet and then into meters. So we know that there are 6,076 feet in 1 nautical mile. And we know that there's 1 meter in 3.281 feet. So the units of nautical miles in the numerator get canceled with the units of nautical miles in the denominator. The units of feet in the numerator get canceled with the units of feet in the denominator. And then luckily, we're left with an answer in meters. So the length of this cube, when you multiply all this together, is 4,814.87 meters. Okay, that's just our length. Now our width, we're going to do the same thing. Right, our width is 1.2 nautical miles. 1.2 nautical miles. And we know that there are 6,076 feet in 1 nautical mile. This kind of makes you appreciate more the unit conversions between kilograms and grams and stuff like that, or kilometers and meters, because it's always a factor of like 10, whereas when you're dealing with feet, you have this weird 6,076 feet thing. I don't know. I don't even know why we still use imperial units, to be honest. So we also know that there's 1 meter, 3.281 feet. And again, the units cancel out. So the units of nautical miles cancel, the units of feet cancel, and again, we're left with an answer in units of meters. So our width is going to be equal to 2,222.25 meters. And so last but not least, we need the depth, which I'll call, D. So the depth of this cube of water is 16 fathoms. So 16 fathoms, right? And we know that there's 6 feet in 1 fathom. 1 fathom like that. And then last but not least, we need to convert from feet into meters. So we know that 1 meter has 3.281 feet in it. The units of fathoms cancel, the units of feet cancel, and we're finally left with an answer in meters. So the depth of this thing is equal to 29.26 meters. Right. So now we have our length, our width, and the depth of this cube in terms of meters. So if we multiply all three of these together, we get the volume of the cube in cubic meters. So let's do that. So the volume of this cube is equal to length times width times the depth. So that's our length of 4,814.87 meters times our width of 2,222.25 meters. I have to move this over just slightly. Right. And finally, we multiply by our depth of 29.26 meters. Apologize for sort of squishing it over in the corner here. So when you multiply all these together, you get, unsurprisingly, a very big number. So the volume in cubic meters is equal to, oh man, what even is that? 313 billion, 77 million, and 461 cubic meters. I can do better than that. So this is our answer to the second problem. All right, now let's move on to the third problem from lecture 1. Scoot down a little bit. So example 3. Right, still from lecture 1. So this problem says the vector A, all right, so now we're doing vector problems. The vector A in the drawing has a magnitude. So in the drawing, and I'll make sure to draw it for this. So the vector A in the drawing has a magnitude. It's a magnitude of 750 units. Problem wants us to determine the magnitude and direction. So determine the magnitude and direction of the X and Y components the X and Y components relative to, so part A says the black axis, and part B says relative to the red axes. Okay, so the associated picture with this, try and draw it to the best of my ability. We have a pair of X and Y axes like this. X, its vertical axis is Y. Then we have an additional pair of axes. Don't let this throw you off too much. So this is going to be x prime. And this is y prime. Hat. And so the vector A points somewhere like this. It's our vector A. And the problem says that this angle here is 30 degrees. And this angle here is 40 degrees. So the problem says determine the magnitude and direction of the x and y components of the vector. That doesn't really make sense. The problem is asking us to find the components of A, you know, in the x and y direction, as well as in the x prime and y prime direction. So don't be thrown off by that too much. Okay, let's begin and see how we go about doing this. To start with, let's look at what we know. So we know that the magnitude of A is 750 units, or whatever that is. I could probably just leave that off, actually. I will. I don't feel like writing that all the time. And the angle, so I'll call it theta, I don't know, black. For the black axes, right? The angle between the positive x-axis and our vector A is 30 degrees. 30 degrees. Let me actually switch over to red. Actually, you know what? Instead of calling this theta black, I might actually just switch up the colors. All right, so this black theta corresponds to the angle between the black axes and our vector A. And this red theta will correspond to the angle between our vector A and our positive x prime axis. So this. So in this case, the angle between our positive x prime axis and our vector A can be written in one of two ways. So starting from the positive x prime axis, right? If we were to go all the way around, let me switch over to this. If we were to start from the positive x-axis, x prime axis, and go all the way around, right, that would be an angle of 360 degrees. But really, for the red axis, in order to hit our vector A, we need to go around and we hit the vector A here, right? So the way that we can calculate this is if we go 360 degrees and we backtrack these 40 degrees, that'll tell us our angle. So this is 360 degrees minus 40 degrees, right? So the angle between our vector A and our positive x prime axis is 320 degrees, right? So as an example, I could have, you know, rewritten it like this. Here's our x prime and y prime axes, right? And according to this vector A is 40 degrees below the x prime axis. So I could have, you know, written it like this, something like that. Right, these correspond to the same picture. Right, and I've said that the angle between our positive x prime axis, this one right here, and our vector A is 360 degrees minus that 40 degrees, right, which is this 320. So I've sort of slipped in a convention when dealing with angles, and the convention is this. When you're starting at the positive x-axis, right, if you're counting an angle from a particular axis, if you go, I did not want to erase that. If you start from that axis and you go counterclockwise, then the angle that you count up is positive, right? So if we start at the x-axis and we go to the y-axis, that's plus 90 degrees. If we go from the y-axis to the negative x-axis, right, we go an additional 90 degrees. So altogether, we've gone 180 degrees. If we keep going, that's 270 degrees. And then finally, 360 degrees right here. Sorry, overshot a little bit. So we can use that convention and note that if we start from the x-axis and we go clockwise, then we're not moving in the positive theta direction, we're moving in the negative theta direction. So for example, going from here, the positive x-axis, clockwise, to the negative y-axis like this, would be minus 90 degrees, right? And then minus 180 degrees, minus 270 degrees, and then finally minus 360 degrees. So the reason why I bring this up is because we can either count our vector A as being 320 degrees if we go counterclockwise, right? We're counting up positive theta. Or we could start at the x prime axis and go clockwise, where our theta is going to be negative. So this is just going to be minus 40 degrees. So our theta for red can also be minus 40 degrees. I just want to let you guys know that this angle and this angle are the same. You can use either one of these and you'll both, and like whichever one you use, you'll get the correct answer, okay? So if you guys have any questions about this, I wouldn't be afraid to reiterate this again. So let's begin. So first we want to find the x and y components for our vector A in this black coordinate system. That's easy. So for the black coordinate system, our x component is going to be the magnitude of A times cosine of the angle between our vector and the positive x-axis. Right? Well, the magnitude of our vector is 750 units times cosine of 30 degrees. So this gives us an x component for our vector A of 649.5. Units. All right, that's the first part of A. Second part of A wants us to find the y component in this black coordinate system. So the y component for our vector AY, our vector A, is its magnitude times sine of theta. All right, so that's 750 times sine 30 degrees. And this gives us a y component for our vector A in this black coordinate system of 375 units. So we found the components of A in this black coordinate system. All right, so that wasn't too bad. We've seen that before. But now we've got this tilted coordinate system, x prime and y prime. And we need to figure out the x and y components of A in this new coordinate system. But that's not too bad. We don't really have to change anything. The hardest part about this was figuring out this angle, right? The angle between our new x-axis, this x prime axis, and our vector A. Once we have this angle, right, the method is still the same. So we just switched to red. So now in this new coordinate system, right, x prime and y prime. So now we're looking at this picture. Our x component is going to be equal to still just the magnitude of our vector A times cosine of the angle between our positive x prime, or our positive, x prime axis, and our vector A. So we could either use 320 degrees, like I mentioned. We can either start from the x-axis, go all the way around until we hit our vector A. Or you can use minus 40 degrees. We can start at our positive x-axis and then go clockwise, which gives us a negative theta. So we can use either one. I'll use minus 40, because why not? This is going to be the magnitude, which is 750 units, times cosine of minus 40 degrees. Right. So this says that the x component of our vector is equal to 74.5 units. Maybe I should switch to a slightly different color. I don't know what's going to be super visible. Maybe this. Yeah, this is not much better, but it's better than green. And so for the y component, it's exactly the same, except now we use sine. Right? The process is still exactly the same as when our coordinate system was what we were used to, right? Where x is along the horizontal direction and the y component stuff is in the vertical direction. It's the same process. Again, the hardest part is just figuring out our new angle. So ay is the magnitude of our vector times sine for angle theta. So it's 750 times sine of minus 40 degrees. And this is going to give us a y component for our vector A in this new coordinate system of minus, right, if we punch all this into a calculator, of minus 482, 2.1 units. Okay, so now let's look at this. Let's look at the answers that we've actually gotten. So if I go back up to our picture and we just look at this, the first part of our problem, I want you guys to notice that both the x and y components of our vector, in this black coordinate system, are positive. This means that it points in the positive x direction, and it also points in the positive y direction. And that kind of makes sense. It's in this first quadrant here. But now, going down to our second coordinate system, right, where x prime and y prime, notice here that the x component is still positive, right, because it still points in the positive x direction. But now our y component is negative. That is, in this new coordinate system, our vector A points downwards. So drawing this picture and getting this result kind of makes us feel a little bit better, because our vector A does point to the right, but it also does point down. So the y component should be negative. And with that, we finish this problem. So the fourth and final problem for the lecture 1 problems is example 4. And this is a vector problem. So example 4 says that we have vector A, which is 3 in the x direction plus 2 in the y direction. We've got a vector B, which is minus 2 in the x direction plus 1 in the y direction. And the problem says that there's some other vector C, which is equal to 2a minus 3 times b. So the problem is asking, well, what is the magnitude of this vector C? What's the magnitude? And it's also asking, in what direction is this vector C pointing in? So let's begin. So first things first, we want to reduce all of this down. So first we're going to do 2 times our vector A. So we have that our vector C is equal to 2 times our vector A, which is 3x, right? 3x plus 2y. And then we have minus 3 times b, but we can turn that minus sign here into a plus -1 times 3 times the vector b. So the vector b is minus 2 in the x direction plus 1 in the y direction. right? And so when we're multiplying a vector by a scalar, we take the scalar, or just the number, and we distribute it through to each component of the vector. So 2 times a becomes, so we have 2 times 3. So this is now 6 in the x direction. And then 2 times 2 is 4. So that's plus 4 in the y direction. Just like that. Then we go over here. So -1 times 3 is -3. And then we're going to distribute that through to each component of b. So we have -3 times -2. This becomes -6 in the x direction. So then we have -3 times 1. This becomes -3 in the y direction. And now all we have to do is add these two vectors together. So the way that we do that is we take their x components and we add them together. And that's, the total amount that c is pointing in the x direction. And then we do the same thing with the y components. We just add those together. So c then becomes, this vector c becomes 6 plus -6, or 6 minus 6 in the x direction. And for the y components, we have 4 plus -3. So 4 minus 3 in the y direction. Well, 6 minus 6 is 0. So this doesn't have an x component. So you either write it like this, or we could just leave this off altogether. And then for our y component, we have 4 minus 3, which is just 1. So plus 1 in the y direction. Okay, so that's not too bad. So looking at this, the magnitude of c is a little redundant because we don't have an x component, but the magnitude of c is the x component squared, so 0 squared, plus the y component squared, all under the square root, right? So we have 0 squared is 0, plus 1 squared, which is 1, so 0 plus 1 is 1, and the square root of 1 is just 1, right? So the magnitude of c is just 1. That's the first part of the problem. And the second part of the problem is saying, what direction is this pointing in? Well, looking at a picture of our axes, so we have the x direction, we have the y direction, and then we have this vector c, which according to this says that it has 0 component in the x direction, so it doesn't point in the x direction, and it points upwards in the y direction by 1. So this is, bring that back. So this is y is equal to 1. Then our vector c starts from the origin and points up like this. So it turns out that c is actually equal to the y hat unit vector. So in this case, we see that c is equal to the y hat unit vector, right? Because it points straight up in the y direction. Now, if we want the angle between the positive x-axis and our vector c, well, note that we have to start from the positive x-axis, and then we have to go 90 full degrees in order to hit the positive y-axis. So it turns out theta in this case is equal to 90 degrees. Or maybe I'll write it like right here. Theta is 90 degrees. So that's it for the first lecture problems. All right, so from this point on, we're going to be looking at lecture 2 problems. So Lecture 2 problems. So lecture 2 deals with one-dimensional kinematic motion, as well as some free fall stuff. So in example number 5 that we're going to see today, example 5, we're talking about a football player. So example 5 says that a football player starting from rest at the line of scrimmage, So we're actually going to leave off the line of scrimmage thing because it's not really important to the problem. So football player starting from rest accelerates along a straight line. Accelerates along a straight line. For a time of 1.5 seconds. For a time of 1.5 seconds. Then, during a negligible amount of time, he changes the magnitude of his acceleration. He changes the magnitude of his acceleration to a value of 1.1 meters per second squared. To a value of 1.1 meters per second squared. So with this acceleration, he continues in the same direction for another 1.2 seconds. He continues in the same direction for another 1.2 seconds. For another 1.2 seconds until he reaches a speed. Till he reaches a speed of 3.4 meters per second. 3.4 meters per second. So the question wants to know, what is the value of his acceleration? What is the value of his acceleration during the initial 1.5 second period? Okay, so there's a lot going on in this problem. So there's really two sections to this problem. In the first section, the football player starts from rest, and then he accelerates along the line for 1.5 seconds. And so that's the first part of the problem. The second part of the problem says that during a negligible amount of time, he changes the magnitude of his acceleration to a value of 1.1 meters per second squared. So this whole during a negligible amount of time, that's just saying he like almost immediately changes his acceleration to 1.1 meters per second squared. So then the problem says that with this acceleration, he continues in the same direction for another 1.2 seconds until he achieves a final speed of 3.4 meters per second. And the question is asking, well, we know what his acceleration is during the second half of the problem, but what is his acceleration during the first half? So start with, let's draw a picture. I got something like this. Is the x-axis. Let's just say that this is x is equal to 0 meters. And he initially starts here with an initial speed of 0 meters per second. 0 meters per second. And then he runs. He gets to a certain point. Let's say it's here. And at this point, total elapsed time, call it delta t1, this will have been equal to 1.5 seconds. So for 1.5 seconds, he's accelerating until he reaches, after 1.5 seconds, he gets to this point. And then he changes his acceleration to something else until he gets to here. So let's say that this is, the end where he gets to. And his final velocity in this case is 3.4 meters per second. Right. And we also know that the amount of time it took for him to get from here, like to a final velocity of this duration, t2 is 1.2 seconds. And the acceleration for this first part, call it a2, or for the second part, excuse me, was 1.1 meters per second squared. And we want to know how fast was he accelerating in the beginning of this problem. So this is a two-part problem where each part is now an example of a constant acceleration situation. So what we're going to do, we're going to make use of the average acceleration equation, which is that the average acceleration is equal to our change in velocity divided by our elapsed time, delta t. All right, so this is just equal to our final velocity minus our initial velocity divided by the elapsed time. Right. And so I'm going to say that the velocity right here, where he switches up the acceleration, maybe switch colors, velocity right here, I'm going to call it V, oh, I don't know, star, because we don't know exactly what it is. We can figure it out. So let's look first at the second half of the problem and then sort of work our way backwards towards the first part. So we know what the acceleration is, the average acceleration for the second half of the problem. That says that a2 is equal to the final velocity minus the velocity that they started with, which in this case, for the second half of the problem, the quote unquote starting velocity was v star, divided by the elapsed time, divided by the elapsed time, which was delta t2, right? And so the acceleration for the second half of the problem was 1.1 meters per second squared, right? Again, all we've done here is use the definition for the average acceleration. So the left-hand side of this is 1.1 meters per second squared, and the right-hand side is equal to the final velocity, which according to this was 3.4 meters per second. 3.4 meters per second minus the initial velocity, which we don't know, call that v star. And that's all divided by the elapsed time. Now for the second half of this problem, delta t2 is 1.2 seconds. So that's 1.2 seconds. And so we can manipulate this equation here to try and figure out what velocity this dude was moving at the point where he decided to change up acceleration. So we can figure out what v star is. And then from there, we can work backwards. So if we multiply both sides of this equation by 1.2 seconds, we get 1.1 meters per second squared times 1.2 seconds on the left-hand side. And then on the right-hand side, we have 3.4 meters per second minus v star. So if I add v star to both sides and I subtract off whatever this multiplication is from both sides, we get that v star, the velocity at the point where the football player decides to switch up his acceleration, that's going to be equal to 3.4 meters per second minus 1.1 meters per second squared times 1.2 seconds. And if you punch all this into a calculator, this gives us a v star of 2.08 meters per second. Just like that. So now that we know how fast the football player was moving at this midpoint here, now we can do the same thing again to figure out his acceleration in the first half of the problem, because we know what his initial speed was, we know what his final speed was for this first part of the problem, right? And we know how long it took. So the rest should be fairly straightforward. So the acceleration in the first half of the problem is equal to his final velocity, which in this case is v star, minus his initial velocity, which was 0. So what's all that? Divided by elapsed time. So up top in the numerator, we have v star minus v naught. So v star is 2.08 meters per second minus v naught, his initial speed when he first started running. So that's just going to be 0 meters per second. It's fairly straightforward. And delta t1 is 1.5 seconds. All right, so 2.08 minus 0 is just 2.08, and that divided by 1.5 gives us our acceleration for the first half of the problem. So 1.39 meters per second squared. And this is what the problem originally wanted us to find out. All right, how fast was this football player accelerating during this first 1.5 seconds? All right, so this next problem is going to be a little bit more morbid, but hopefully that's okay. So this was example 5. All right, so now we're on example 6. Example 6. There we go. So example 6 says that a cement block accidentally falls from rest. Accidentally falls from rest from the ledge of a 53-meter high building. 53-meter high building. When the block is 14 meters above the ground, when the block is 14 meters above the ground. A man who is 2 meters tall, 2 meters tall, it's very tall, looks up and notices the block, looks up and notices that the block is directly above him. Block is directly above him. How much time, at most, does the man have to get out of the way? So how much time at most does the man have to get out of the way? Okay. Let's draw a picture. So got our building. We have a building like this. And this is going to be our ground. So the building itself, this whole thing, is 53 meters tall. And we have a dude who's 2 meters tall down here. Let me actually place him on the ground. There we go. So this person is 2 meters tall. So a rock starts from the top of this building and it accidentally falls to right about here, let's say. So it starts falling from here. And when it gets to this point, which is 14 meters off the ground, this distance here, it's 14 meters. So when it gets to that point, the man notices that the rock is falling. So the initial velocity of the rock is said to be 0 meters per second. And it starts falling from rest. And here it's falling with some velocity we'll call v1. And so how much distance is there between when the man notices the rock and the man himself? So in this case, it's going to be these 14 meters, right, this distance here, minus the 2 meters that the man is tall because, you know, he doesn't want to get hit in the head. So that's going to be 14 minus 2 meters, or 12 meters. So this rock only has to go 12 meters in order to, you know, bonk this guy on the head, which is not good. So we need to figure out first how long it takes this block to fall from its initial starting position to when the man notices the block 14 meters above the ground. All right. So I'm going to draw another picture to sort of help us. So that's the ground. Let's say that this right here is 2 meters above the ground. Right, so this distance here is 2 meters. Let's say that the velocity of the rocket at this point, let's call it v2, and 14 meters above the gentleman right here. it's 14 meters. 14 meters above the gentleman. Like we've listed in this diagram here, this little picture here, the rock is moving at a speed v1. v1, right? And so we're going to try and find out how much time there is, switch colors, how much time there is between these 2 points. These 2 points. Okay, so to do that, we need to find V1, we need to find V1 and V2. So the way that we're going to tackle this is by using the fact that our final velocity squared minus our initial velocity squared is equal to 2 times our acceleration in the y direction, which in this case is just the acceleration due to gravity, times the displacement. Okay, so let's try and find V1 first. How fast is the rock going when the man first notices it 14 meters above him? So in that case, on the left-hand side, we have V1 squared minus the initial velocity, right? But the initial velocity is just 0 because it's starting from rest up here. So it's 0 meters per second. It's going to be equal to 2 times the acceleration due to gravity, which is minus 9.8 meters per second squared, multiplied by our displacement in the y direction. So if this whole thing is 53 meters, the displacement is going to be from 53 meters down to here. So it's going to be our final position, which is 14 meters, minus our initial position of 53 meters. So in this case, the displacement is going to be minus 39 meters. Right, where the minus sign indicates that indeed this thing has fallen downwards. Right. So 0 squared is just 0. So if I take the square root of both sides, we get that V1 is equal to the square root of the right-hand side. So the square root of 2 times negative 9.8 times negative 39. And this is going to be equal to 27.65 meters per second. But remember that this thing is falling downwards, so its velocity must be negative. So we need to add in this negative sign here. All right, so that's V1. Now for V2, we're going to do the same thing. So we have V2 squared minus the initial velocity squared. But the initial velocity squared is still 0. It's equal to 2 times the acceleration due to gravity, right, times the displacement for V2. Now V2 is 2 meters above the ground. Right, so that V2 is 2 meters above the ground. So the total displacement is going to be 53 minus 2, or 51 meters downward. So the displacement is going to be minus 51 meters. Minus 51 meters. Right, 0 squared is just, 0. So if we take the square root of both sides, we get that V2 is going to be equal to 31.62 meters per second. And we have to remember that since this thing is falling downwards, we need to put back in a negative sign here. So now we have V1 and V2. Now we can figure out how long it takes for the cement block to go from 14 meters above the dude to 2 meters above the dude, which is basically his head. Okay, so the way that we're going to do that is by noting that the acceleration is equal to the change in velocity of an object divided by the elapsed time. So in our case, we know what the acceleration is, right? The acceleration is just the acceleration due to gravity. It's minus 9.8 meters per second squared. We figured out what V2 and V1 are. So the right-hand side, V2 minus V1 in this case. And we're looking for delta t. So if I multiply both sides by delta t and divide both sides by the acceleration a, we get that the time it takes from when the man first notices the cement block is equal to V2 minus V1, right, all divided by the acceleration due to gravity. Right, now we just plug some stuff in. So this is going to be minus 31.62 meters per second minus V1, which is again minus 27.65 meters per second. All that is going to be divided by minus 9.8 meters per second squared. And we get a delta t, right? The time that the person has to move out of the way before he gets, smooshed, that's going to be equal to 0.41 seconds. And there's our answer. So now it's time to move on to lecture 3 problems. Lecture 3. All right, this last example we did is example 6. This next problem will be example 7. All right, so example 7 talks about a spaceship. So on a spaceship, 2 engines, fire for a time of 565 seconds. The problem says that 1 gives the craft an acceleration in the x direction. So I guess 1 engine gives the craft an acceleration. An acceleration in the x direction. Of ax is equal to 5.1 meters per second squared, while the other produces an acceleration in the y direction. So while the other engine produces an acceleration in the y direction. Of ay is equal to 7.3 meters per second squared. So at the end of the firing period, the craft has a velocity. The aircraft has velocity components. Craft has velocity components. Of bx is equal to 300 or 3,775 meters per second, and a y component vy of 4,816 meters per second. 4,816 meters per second. So the problem wants us to find the magnitude and direction. Find the magnitude and direction of the initial velocity. There we go. The problem wants us to express the direction as an angle. Angle respect to the positive x-axis. It's kind of a long problem. All right, so this is an example of a constant acceleration problem. So the way that we're going to solve this is by noting that we have the accelerations, right? We have the time span with which these engines are firing, right? We know how long that the ship is accelerating for. And we know the final x and y components for our velocity vector. So if we use the x is equal to the initial velocity's x component plus acceleration in the x direction times time, and final y component is equal to our initial velocity's y component plus acceleration in the y direction times time, then we can use this to figure out what the x and y components for our initial velocity are. So let's write down a little bit about what we know. So we know that the time that these engines are firing is 565 seconds. Just like that. We know that the final, or that the acceleration in the x direction is 5.1 meters per second squared, and that the acceleration in the y direction is 7.3 meters per second squared. And then we know that our final velocity in the y direction, or excuse me, in the x direction, is 3,775 meters per second. And last but not least, we know that our final y component for our velocity is 4,816 meters per second. Okay, so looking at this first equation here, we're going to try and solve it for the initial velocity's x component. So on the left-hand side, we have our final velocity in the x direction. 3,775 meters per second. And on the right, we have the x component for our initial velocity vector plus our acceleration in the x direction, which is 5.1 meters per second squared, times our time of 565 seconds. Right. And then for the y component equation, right, we have our final we have the y component for our final velocity on the left-hand side, so 4,816 meters per second. On the right, we have our initial velocity, so y component, plus the acceleration in the y direction, which is 7.3 meters per second squared. Again, times our time. Now, if I subtract this equation or this term off from both sides, we get the x component by itself. And for this equation, if I subtract this term off from both sides, I get the y equation by itself. So when you do that, you get the initial velocity in the x direction is given by 893.5 meters per second. And then for our y stuff, the initial velocity vector's y component, it's going to be equal to 691.5 meters per second. All right. But we're not done because the problem wants us to find the magnitude and direction of this initial velocity vector. So let's do that. Well, the magnitude is straightforward because we know that the magnitude of a vector, for example, our velocity vector, is going to be equal to the x component squared plus the y component squared all under the square root. And we know what the x and y components are for our initial velocity vector. So the x component for our initial velocity vector is going to be 893.5, 893.5 meters per second. We're going to square that, plus our y component squared, which is 691.5, 691.5 meters per second squared. All right, we just take the square root of that. And so if you punch this into a calculator, we get the magnitude for our initial velocity vector is equal to 1,129.8 meters per second. All right, so that's the answer to the first part of the problem. Now, the second part of the problem was asking about the direction of the vector, right? The initial velocity vector. And so I want you guys to notice that our x component for our initial velocity is positive, and our y component for the initial velocity is positive, which means that if we draw this little picture here, right? So the vertical axis is a y-axis, horizontal axis is the x-axis, right? The fact that the x and y components of our initial velocity vector are both positive means that it's pointing in the first quadrant. So our initial velocity vector might look like something like this, right? And so the angle that it's trying to ask us to find is this angle theta right here. So we can find it by noting that tangent of theta is equal to, and if we make a right triangle like this, then the opposite side length is the y component for our initial velocity vector. The adjacent side is the x component for our initial velocity vector. And tangent of theta is equal to initial velocity's y component divided by the initial velocity's x component, which looks like that. Right. And so now, if we take tangent inverse of both sides, we get tangent inverse of tangent of theta on the left. On the right, we have tangent inverse. And now here we're going to input the y and x component for our initial velocity vector. So the y component is 691.5. And our x component is 893. 0.5. And so the left-hand side is tangent inverse of tangent of theta, which just gives us back theta. On the right-hand side, we have tangent inverse of 691.5 divided by 893.5. Right? If you take this and you punch into a calculator, the calculator is going to spit out that this is an angle of about 37.7 degrees. So there we go. We have both the magnitude as well as the direction for our initial velocity vector. So this angle here is about 37.7 degrees. So now let's move on to our last problem of the day. So the last problem we did was example 7. So this will be example 8. So example 8 says that a ball is thrown upward. A ball is thrown upwards at a speed v naught. At a speed v naught, so we don't really know what it is. At an angle of 52 degrees above the horizontal. At an angle of 52 degrees above the horizontal. Right, which is the positive x-axis. Problem goes on to say that it reaches a maximum height. It reaches a maximum height of 7.5 meters. So the problem's asking, well, how high would this ball go if it were thrown straight upwards at a speed v naught? So how high would this ball go if it were thrown straight upwards at a speed v naught? So what we can do here is try to solve for the y component for our initial velocity in terms of its magnitude v naught, as well as its trigonometric function. So in this case, theta is 52 degrees, and its max height delta y is 7.5 degrees, or 7.5 meters, excuse me. Okay, so at the max height, right, the y component of our velocity has to be 0. So if we use Vy squared minus the y component for our initial velocity vector squared, that should be equal to 2 times our acceleration in the y direction times our displacement like this. Right? Now at max height, the y component for our velocity should be 0. So we have 0 meters per second squared minus the y component for our initial velocity vector squared. But remember that the y component for our initial velocity, we can get that by the magnitude times sine of 52 degrees squared. Right, this is just how we calculate the y component for our initial velocity vector. And on the right, we have 2 times minus 9.8 meters per second squared. Move this over a little bit. Times our maximum height of 7.5 meters. So on the left-hand side, we have 0 squared minus this stuff squared. So the left-hand side becomes minus V naught squared sine squared 52 degrees. And then on the right, we have 2 times negative 9.8 times 7.5, which is minus 147. And this is going to have units of meters squared per second squared. Right. And since we have a minus sign on both sides, we can multiply both sides by -1. Take rid of the negative signs. And then what we can do is we can divide both sides by sine squared of 52 degrees. So then we have our initial velocity, magnitude squared. That's going to be equal to 147 divided by sine squared for 52 degrees. It's going to be in units of meters squared per second squared. And last but not least, if we take the square root of both sides, we see that our initial velocity, the magnitude of it at least, is 15.39 meters per second. All right. So now we're going to throw it straight upwards. So now we're throwing it straight up, right? Then we can use the same equation. It says that the velocity in the y direction squared minus our initial velocity in the y direction squared is equal to 2 times our acceleration is equal to 2 times our acceleration times our displacement in the y direction. So just like before, our the velocity in the y direction at max height is going to be 0. So this term is still 0 squared. But now our initial velocity in the y direction, well, our initial velocity in the y direction is just 15.39 meters per second because we're directing all of that magnitude directly straight upwards. We're no longer firing at an angle. So the y component for our initial velocity vector is what we just found to be 15.39 meters per second. We're going to square that. And on the right hand side, we have 2 times the acceleration times delta y. And so the problem's asking us to find delta y. So 0 squared is still 0. And the left-hand side becomes minus 236.85 meters squared per second squared. On the right-hand side, we have 2 times negative 9.8, which is minus 19.6 meters per second squared times delta y. Now, if we divide both sides by 19.6, we get delta y by itself, which again is the max height. So delta y, the max height, if we were just to throw this straight up, is 12.08 meters. And so that's our final problem for today. If you have any questions at all, please feel free to ask. I'm also available for email if you guys want to email me. I will try and keep an eye on my email as we get closer and closer to tomorrow. So that being said, see you guys tomorrow.